When doing numeric integration, we are trying to solve a problem of a type which is fairly common in mathematics, namely the following. Let's say we have a problem and we want to solve it as is the usual mathematical custom exactly. So what we want to do is we want to get the bullseye and get the exact solution of that problem. But if you play darts or if you have played them at all, you know that that's not always possible. And sometimes it's even not advisable to put all your effort into trying to get something exactly. It may be much better instead to say, all right, I cannot hope to be able to get the bullseye. Well, let's do something a little bit different. Well, let's adjust as we go along and let's hope that we find a way of getting close enough. That is what we're going to be doing with the integration. So the idea will be to try and get an approximate answer in situations where the exact answer is not possible. So here is the key question about integrals that we're going to be looking at, and we're trying to do the best we can in a situation where we cannot get the exact value. That is the following. How can we compute a definite integral? Well, we know how to do that. All we need to do is basically apply the fundamental theorem of calculus, compute an antiderivative, evaluate the antiderivative at the two limits, and we're done. Fine, but what if the fundamental theorem does not work in the sense that we cannot compute an antiderivative? Remember, computing an antiderivative is not always easy, sometimes it's difficult, and sometimes it's even impossible. So what do we do when we cannot rely on the fundamental theorem of calculus, and yet we need to find some kind of value for this definite integral, because maybe it comes from one of the applications we've just seen? Well, what we're going to do is we're going to approximate instead. Well, how are we going to approximate? What kind of methods do we have? Well, we have actually already a method which relies on the very definition of a definite integral. Remember, the definite integral from a to b of some continuous function f of x dx, by definition, not by the fundamental theorem, but by definition, is the limit as n goes to infinity of the sum from 1 to n of f of x I delta x. And I hope I don't have to refresh your memory on what the meaning of all those symbols are. Alright, so the key point here is that the last step that we need to do is compute the limit, and that last step creates a problem. If you remember from the definition, computing that limit can be very, very difficult. Fortunately, the fundamental theorem of calculus allows us to get around that by computing antiderivatives. But what can we do when the FTC cannot be applied and the limit is too tough? Well, we're simply not going to compute the limit. So what we're going to say is, well, that's going to be approximately equal to simply the sum from 1 to n of those products f of x I delta x. So we're going to do the three steps of computing the integral, namely slice, approximate, and add up, but we're not going to compute the limit. In this case, what we're using is what we can call the Riemann sum method. And we're going to see, first of all, how to use this Riemann sum method in a systematic and hopefully efficient way. Before I show you what the systematic and efficient way of using the Riemann sum is, let me bring up a couple of issues here. In fact, two issues. And these have to do with the choices that we have in trying to approximate a definite integral by using the Riemann sum. First of all, we need to decide, well, how many intervals do we choose? Remember, it's the sum from 1 to n. Well, what do we choose as our number n? Now, notice that, again, theoretically, the bigger the n, the closer we can get to the integral. And so theoretically, we can get as close as we want to the value of the integral by taking n to be large enough. But how large is large enough? Well, in practical terms, just as many as is feasible. So pick n large enough that you can actually compute it, but not too large that you can get crazy. Now, if you do it by hand, that will pretty much mean no more than 6 intervals. If you can rely on some computer program, or you can design your own program to implement this Riemann sum, you can go higher to 1,000 or 1,000,000 or whatever, but it really depends on the capability of the calculating machine you have. The second issue is, all right, in each one of the intervals that we're using, what value of x do we pick? Theoretically, we can pick anything, so any choice will actually work. And in fact, if we make a choice and it doesn't give us a good approximation, then what we can do is we can pick a different choice. Or what we can do is we can use the same criterion for our choice, but increase the number of intervals. So in theory, any choice will work. But there is one method which turns out to be fairly efficient for fairly simple reasons, and that is to use the midpoints. Okay? The fairly simple reason is that by using the midpoint, we're going to end up making some kind of averaging. Remember, what we do is we slice, we approximate. Well, if we approximate by using the midpoint, that approximation is going to work fairly well generally. We're going to see how well at the end of this class.